Welcome to The Explainer. Today, we're jumping right into a huge question in the digital world. We're going to tackle how you can create money that can't be counterfeited when it's just made of data that can be copied over and over again. We'll explore how a network of total strangers can somehow agree on the truth, and in doing so, solve a problem that stumped computer scientists for decades. So let's start with that fundamental challenge. The ability to copy digital information is usually a feature, right? You can send a photo to a million people and the original is still there. But for money, well, that's not a feature. It's a catastrophic bug. If you can just copy-paste your money, it's completely worthless. And this bug, this fundamental flaw, has a name. It's called the double spending problem. Now, for anyone who's familiar with relational databases, think of it like this. How do you stop someone from making an unauthorized copy-paste of a row in your transaction table? How do you guarantee a unique digital asset isn't just duplicated and spent in two different places at the same time? Let's break that down a bit. Imagine you have one digital coin. You could try sending that exact same coin to two different people at basically the same time. Now, if both of those transactions are seen as valid, you've just created money out of thin air. You've counterfeited it. Any system where that's possible would just collapse instantly because no one would trust the money. Okay, so in the traditional world, the solution to this is pretty straightforward. A central authority. Your bank keeps one master ledger. If you try to spend the same dollar twice, the bank sees the first transaction go through and just rejects the second one. Simple. But this creates its own massive vulnerability, a single point of failure. If that central server gets hacked or just goes down, the whole system is at risk. And that really leads us to the billion-dollar question. Without a central referee, without a bank in the middle, how does a distributed network of computers, none of which trust each other by the way, prevent cheating? How can they all agree on a single source of truth? Basically, how do they do the job of a bank without a bank? The answer is a really elegant concept called a consensus mechanism. You can think of it as a protocol, just a set of rules, that allows a group of participants who don't trust each other to collectively agree on and maintain a shared reality, all without anyone being in charge. And what is it they all need to agree on? Well, it really boils down to one simple but crucial thing: the order of transactions. To stop double spending, the entire network has to establish a single shared history and say, okay, this payment happened first, which means any other attempt to spend that exact same digital coin is invalid. Period. This is a classic problem in computer science, and there's a fantastic analogy for it. It's called the Byzantine generals problem. Imagine you have several generals surrounding a city. They have to coordinate an attack, but they can only communicate by sending messengers. The catch? Some of those generals might be traitors, sending false information to sabotage the plan. How do the loyal generals agree on what to do? That is the exact problem a peer-to-peer network faces, achieving consensus even with untrustworthy participants. So, how do you solve this Byzantine generals problem in the digital world? Well, the ingenious solution, first implemented by Bitcoin, is called proof of work. It's a mechanism that completely flips the script. It replaces trust with something much, much more reliable: verifiable work and good old-fashioned economic self-interest. So, how does that actually work? How can work replace trust? Here's the core idea. To earn the right to add new transactions to the ledger, participants, we call them miners, have to prove they've spent real-world resources. They're forced to do computationally expensive work that costs actual money for hardware and electricity. And by doing that, the system brilliantly aligns their incentives. All of a sudden, being honest becomes the most profitable strategy. Okay, let's walk through what this competition looks like. So miners gather up a bunch of pending transactions into a block. Then they all start a race to solve a really hard mathematical puzzle. They're essentially trying to guess a specific number that, when you combine it with the block's data, produces a special cryptographic pattern. The first one to find that number wins, broadcast their block to everyone, and if it's all valid, they get a reward. And believe me, this is expensive. Massively so. We're talking huge investments in specialized hardware and enormous electricity bills. And that expense? That's the economic engine that secures the whole network. Mining isn't some casual hobby, it's a capital-intensive business. And that investment acts like a security bond. If a miner tries to cheat and their block gets rejected, they lose all the money they just spent on electricity and get absolutely nothing in return. So this process secures each individual block of transactions. That's cool. But how does that create a permanent, unchangeable history? Well, that's the next critical piece of the puzzle. The real genius here is in how these blocks are all connected together. So, how are they linked? It's pretty clever. When a winning miner creates a new block, it's not just a list of transactions. It also contains a unique cryptographic fingerprint, what's called a hash, of the block that came directly before it. So it's literally like a digital chain. This link forges what we call a blockchain. Each new block doesn't just connect to the last one, it cryptographically seals the entire history of every single block that came before it. Now, think about what it would take for an attacker to go back and change something in the past. To alter an old transaction, they wouldn't just have to redo the work for that one block. They'd have to redo the work for every single block that's been added since then, and they'd have to do it all faster than the entire global network is adding new honest blocks. It's like trying to rebuild the foundation of a skyscraper while thousands of workers are still building new floors on top. It's basically impossible, both computationally and economically. But what happens if two miners solve a block at almost the exact same time? How does the network choose which one is real? This leads to a beautifully simple rule for keeping everyone on the same page. If two different versions of the chain appear for a moment, everyone in the network just agrees to follow the longest one, the one that has the most computational work invested in it. This ensures that the network always, eventually, comes back to a single shared history. So let's put it all together. There you have it. By combining a shared public log, expensive computational work, and really powerful economic incentives, this system solves the double spending problem without needing a central bank. It creates a transaction history that's totally transparent, ridiculously expensive to attack, and for all practical purposes, completely irreversible. And all of this leaves us with a pretty fascinating final question to think about. What's actually more trustworthy? A single, powerful institution with a single point of failure, or a global, decentralized network where the truth is just an emergent property of transparent rules, verifiable math, and shared economic self-interest? If you found this breakdown helpful in any way, we'd really appreciate it if you'd like, share, and subscribe for more deep dives. Thanks for joining us.